If you drop a heavy, CPU-bound machine learning model straight into a standard web framework, you create an immediate bottleneck. The moment a traffic spike hits, the server's request handling threads lock up, bringing the entire system to a dead stop. To solve this, we are going to build a production-ready Sentiment Analysis API from the ground up, utilizing FastAPI, HuggingFace, and Redis. We have to clear two specific hurdles to make this work: engineering computational efficiency, so we aren't wasting server cycles, and building in infrastructure stability so the endpoints don't crash under load. Moving an experimental data science notebook into a reliable Tier 1 production API requires engineering-specific bypasses for these bottlenecks. Here is exactly how we do it. Step 1 is looking at how FastAPI routes incoming HTTP traffic. It relies on Python's asynchronous model, which uses a single-threaded event loop to handle concurrent network requests. Model inference requires heavy matrix multiplication on the CPU. If you execute that synchronous calculation directly on the event loop, you block the thread for the duration of the inference. While the model is thinking, the API is deaf to any other users. The architectural fix is to isolate the HuggingFace model execution, pushing it out of the main event loop and into a dedicated background worker thread pool. This code snippet shows the separation. By wrapping our model prediction call inside the run-in-executor function, we hand the heavy math over to the background thread. The event loop remains entirely free to accept new incoming HTTP traffic. Offloading these heavy calculations to thread pools is the only way asynchronous web servers can survive synchronous AI tasks. Now that the API can handle concurrent traffic, we need to eliminate computational waste. Users frequently submit identical text strings. Running a neural network from scratch on the exact same input repeatedly wastes massive amounts of compute time. We introduce Redis as a distributed memory interceptor to bypass the model entirely. We hash the incoming text string and check Redis to see if we've already saved a prediction for it. But caching every unique string forever introduces a fatal flaw. Eventually, the server will store so much data that it runs out of memory, causing an OOM crash. This diagram illustrates how we solve memory exhaustion. We apply a Time-To-Live, or TTL, configuration on our cache keys. When a specified time window expires, the oldest data blocks automatically dissolve from memory before the bucket overflows. By combining Redis with a strict TTL, we shift the system's main bottleneck from an expensive CPU calculation to a highly efficient self-cleaning memory lookup. With our caching in place, we still have to protect the endpoints themselves. Malicious scrapers or accidental traffic spikes from internal microservices can easily overwhelm unprotected AI infrastructure. We store incoming request timestamps in a Redis sorted set, dropping them as distinct points into a 1-minute window. As time progresses, the window shifts forward, dynamically dropping older request data outside the timeframe. However, there is a vulnerability here known as a race condition. If a bot sends hundreds of concurrent requests, standard counters might allow them through before registering the limit. To prevent this, we wrap validation logic in a Redis pipeline, bundling commands into a single execution. The instant the limit is reached, access shuts off. True infrastructure stability requires these mathematical guarantees against concurrency. Simple counters will fail under heavy load. Next, we deploy the application using Docker. Python machine learning libraries require heavy C++ build tools to compile, which creates a massive file size footprint. We address this by using a multi-stage Dockerfile strategy. We do the heavy compiling in an initial builder environment, then copy only the finished code into a fresh, minimal production environment. Stripping out those compilers and caching artifacts reduces the final production container size from over 3 GB down to just 500 MB, an 80% reduction. Omitting these build artifacts from the final image drastically improves network deployment speeds and shrinks the surface area for security attacks. Now that the architecture is built, step 1 of our verification is to bring the full Docker Compose stack online. Step 2 is validating system readiness. We ping the /health endpoint, confirm the server is up, and ensure the model has loaded. Next, we execute a standard post-prediction request. The initial cold start CPU calculation runs the model, establishing our baseline inference latency at around 150 milliseconds. This terminal output shows the exact same request executed immediately afterward. The true cached flag confirms a sub-millisecond cache hit, completely bypassing the model. Now we test input validation by sending an empty text string to the endpoint. The API correctly rejects it with a 422 unprocessable entity error, preventing bad data. To test our rate limiter, we launch a rapid, automated loop of requests, intentionally sending more traffic than the threshold allows. The system's defensive response kicks in exactly on time. It rejects excess traffic with a 429 status code and a precise retry after header. Finally, we run the automated PyTest suite. Every test passes, formally verifying the underlying logic of our caching and rate limiting services. Successfully passing this sequence of tests guarantees the API is fully equipped for real-world production traffic. We have constructed a highly resilient API. We bypassed CPU bottlenecks with asynchronous thread pools, mitigated latency through TTL-backed Redis caching, stopped abuse with atomic weight limiting, and ensured fast deployments with minimal containerization. These specific concepts closely mirror the foundational engineering patterns used globally by major tech companies to serve large language models at scale. You can access the repository link below to review the code structure in detail and run the Docker containers locally on your own machine. Mastering these backend principles is the dividing line